Welcome all. In this class, we will discuss the topics of conductors, dielectrics, and capacitance in the unit 2 of electrostatics. So first, we will define about the what do you mean by current, current density, and how to express the continuity equation. Current is nothing but flow of charge. Okay, so current is the flow of charge, as we all know. So electric charge in motion constitutes currents. That means rate of flow of charge per unit time. So I equal to dq by dt. I equal to dq by dt, and this is called defined as the current. Flow of charge is called the current. Now do you define current density? Current per unit area is called the current density. Okay, so current density is measured in ampere per square meter per unit area. So ampere per square meter. Now you consider the increment of current IA. Consider a small current, differential current del I, crossing an small area, surface area del S normal to the current density. So del I equal to Jn current density into surface area. So Jn into del S. So del I equal to J into del S. If you integrate, now total current is obtained by integrating. So I equal to integral surface integral J dot ds. I equal to surface integral J dot ds. So this is the relation between current and current density. Okay. So I equal to dq by dt and J equal to surface integral J dot ds. So this diagram shows the charge. So the movement of charge. So here the charge del q is equal to rho v del v, where del v is a volume, differential volume, which is the product of del s into del l. Okay. Now consider this charge is moving with a velocity v. This charge, so it has traveled through a distance of del x. So it has traveled through a distance of del x with velocity v. Okay, so Vx represents the x component. It is moving in the x direction. So Vx represents the x component of the velocity. So Jx equal to rho v into Vx. So rho v is the charge density and Vx is the velocity. Vx is the velocity. So J equal to rho v into V. We call this current a convection current. And J or rho v is a convection current density. So this is the convection current density. And the current through the closed surfaces, previously we have seen that I equal to J dot ds. So this is, we have right, I equal to J surface integral J dot ds. So by but this, the net flow of current should be equal to the rate of decrease of charge inside the surface. So the outward flow of current should be equal to the already existing charge inside the surface. So these two are of opposite sign. Okay. So the rate of decrease is minus dq by dt. So the principle of conservation of charge. So the principle of conservation of charge requires I equal to surface integral J dot ds equal to minus dqi by dt. This is called the continuity equation. So this equation, that is I equal to surface integral J dot ds equal to minus dqi by dt. This is called the continuity equation. Equation 4 is the integral form of continuity equation. And the differential form or point form is obtained by applying the divergence theorem. So point form can be obtained by applying divergence theorem. So what is divergence theorem when you apply J dot ds? Del dot j dv. So this is the divergence theorem for integral J dot ds. So del dot j dv equal to minus d by dt volume integral rho v dv, because minus dq by dt. So by continuity equation we have minus rate of decrease of charge. So minus dq by dt. So minus dq by dt here. So we have dq is rho v dv, since we are considering volume charge, rho v dt. So since this is constant, we can replace this as partial derivatives. So minus dou rho v by dou t dv. So taking this integral on both sides, we have del dot g equal to minus dou rho v by dou t. So del dot j equal to minus dou rho v by dou t. This is called the point form of continuity equation. Del dot j equal to minus dou rho v by dou t, whereas the integral form is I equal to surface integral J dot ds equal to minus dqi by dt. So we have two point form and integral form of continuity equation. Okay, so we have discussed about current, what is current, what is convection current, convection current density. The unit of our current density is ampere per square meter. Then we discussed about the continuity equation, point form and integral form. Next we will discuss about the conductors and insulators. So conductors, in conductors the valence band smoothly merges into the conduction band. So you look at this diagram. So this diagram shows the energy band structure of the conductor, insulator and the semiconductor. In the conductor, the valence band and the conduction band merges. So there is overlapping of the valence band and the conduction band. Whereas in the case of insulator, there exists a large energy gap between the valence band and the conduction band. And in the semiconductor, there is some minimum energy gap between the valence band and the conduction band. This is how the energy band structure of the three materials, that is conductor, insulator and semiconductor. Okay. In case of conductors, the valence band smoothly merges into the conduction band. So additional kinetic energy may be given to the valence electrons by external field, result in an electron flow, external flow of electrons. Okay. So this force, free electrons move under the influence of the electric field. So this, suppose the electric field is E and the charge is minus E, Q equal to minus E, then it will experience a force called F equal to minus E into E. Okay. If it is free space, the electron would accelerate and continuously increase its velocity and energy. But with the case of conductors, due to the crystalline material, the progress of electron is impeded or is restricted by the collisions with the crystalline lattice structure. So crystalline lattice structure, and as soon as time passes, a constant average velocity is attained. So this velocity is called the drift velocity. Then this drift velocity is linearly related to the electric field intensity by the mobility of electron in the given material. So Vd equal to minus mu E into E. But this mu E is called the mobility of the electron in the given material. For different type of materials, the mobility varies. Say for example, aluminium, it is 0.0012. The mobility is value is aluminium, and for copper it is 0.0032, like that. The mobility varies for different types of materials. Vd equal to minus mu E. So also we have derived already Jx equal to rho v Vx. So now you replace Vx with minus mu E. Okay. So minus rho E mu E. Also as per point form of Ohm's law, J equal to sigma E. So this is called the point form of Ohm's law, where sigma is the conductivity and the current density is related to the conductivity of the material with the electric field intensity. J equal to sigma E, which is called the point form of Ohm's law, where sigma is the conductivity in units is Siemens per meter and E is the field intensity. As we know, its unit is volt per meter. So J is the current density. This equation is called the point form of Ohm's law. And these are the conductivity values, 3.8 to 10 power 7 for aluminium, like that. Okay. Now you analogy of these two equations. That is, analogy of these two equations, we can relate conductivity as sigma equal to minus rho E mu E. Sigma equal to minus rho E mu E. Okay. Now I equal to Js. You know I equal to Js, and also V equal to AL. Equating these two, J equal to I by S equal to sigma E equal to sigma V by L. Also now we know V equal to IR. So here V equal to IR. So here from this V equal to IL by sigma S. IL by sigma S. So relating these two, we have R equal to L by sigma S. R equal to the resistance is related to the inverse of the conductivity. Resistance is the inverse of conductivity. L length of the conductor and S is the surface area. L by sigma S. Okay. Next, what are the characteristics of good conductor? So within a conductor is zero charge density. Always the charge resides in the surface of the conductor, and within a conductor is zero charge density. A surface charge density resides on the exterior surface. The electric field intensity within the conductor is zero. Both the charge density and also the electric field intensity within a conductor is zero. And there are three types of current: conduction current, convection current, displacement current. And the equation for conduction current is J equal to rho v V, that is drift velocity, okay, into charge density into drift velocity, J equal to rho v V, and this obeys Ohm's law. Convection current is the current produced by the electrons in an insulating medium, which is given by sigma E, J equal to sigma E, and this is the point form of Ohm's law. And next one is displacement current, which is given by dou D by dou T. This displacement current is defined as the current flow as a result of time varying electric field in dielectric material. So this occurs in dielectric material, which is given by dou D by dou T ampere per square. So three types of current densities are conduction current, convection current and displacement current. So this happens in conductors and this in insulators. Both of these are in dielectrics. Next, boundary conditions. We'll derive boundary conditions for conductor free space boundary. So to derive the boundary conditions for a conductor, for the interface between conductor and free space. So here we have the conductor, here we have the free space. So what is the field intensity? What is the boundary conditions? So to derive the boundary conditions, we are considering a closed loop path for the tangential component. To derive the tangential component, we have to use a closed path, and to derive the normal component, you consider a cylindrical surface, Gaussian surface. So these are the terms we have to use. So first, to find the tangential component, use a closed path A, B, C, D, A with width del V, del W and height del H. And to find the normal component, consider a Gaussian surface with surface area del S and height del H. Okay. So the field in the tangential component are ET, E and E field component, and the flux density are dt, dn and d. So take this diagram. Now we'll derive the boundary conditions. So as for you know that the electric field intensity around a closed path is equal to 0. That means E dot dl equal to 0. So consider AB plus BC plus ED plus DA equal to 0. So if here we replace ET del V minus En half del H plus En half del H. So remember here the height is del H. So half height above the in the free sphere and half height in the conductor. Okay. So these two terms will be, as del H tends to 0, these two terms will be 0. So we have ET del V. ET del V equal to 0, or the tangential component is 0. Therefore ET equal to 0. This is one of the boundary conditions. Next, consider the Gaussian surface. So d dot, also we have d dot ds equal to C. So consider the Gaussian surface and use the Gauss law, that is d dot ds equal to Q. So here in the cylinder we have three surfaces: top, bottom and lateral surfaces, side surfaces. So top, bottom, sides equal to Q. So the bottom and sides, bottom resides in the conductor. So bottom resides in the conductor. So the field there is 0. So field there is 0, and also sides also will be 0. So we have only top surface, flux emanating from the top surface. So dn del S equal to Q equal to surface charge, so rho S del S. So that means rho S and del S will be cancelled. dn equal to rho S. So we have dt equal to Et equal to 0 and dn equal to rho S equal to epsilon 0 En. So these are the desired boundary conditions for the conductor free space boundary in electrostatics. So the 3 points to be considered are: the static electric field intensity inside a conductor is 0. The static electric field intensity at the surface of the conductor is everywhere directed to the normal to that surface. The conductor surface is an equipotential surface. Next, coming to the nature of dielectric materials. So dielectric materials are composed of dipoles. Dipoles, as we know, positive and negative charges separated by small distance. They are called bound charges because they are not free. They are called bound charges, and these bound charges are another source of electrostatic field. And these dielectric materials, one of the important characteristics is that they are able to store electrical energy. So how this electrical energy is stored means by means of shift of relative positions of the internal positive and negative charges. So dipole exists in the dielectric material. So these dipoles, the storage takes place. Okay. So we have two types of molecules: polar molecules and non-polar molecules. Polar molecules have permanent displacement between charges, while non-polar molecules does not have dipole arrangement until after a field is applied. Okay. And the dipole moment is given by P equal to Q into D. So this we have seen in the previous class itself. Dipole moment is Q, charge Q, any one of the charge, plus Q or minus Q. So it's a charge Q and product of distance, D is the distance. Okay, so this is the dipole moment. And the polarization, if we consolidate the dipole moment over a volume, then the total is called the total dipole moment. This is the total dipole moment, and the total dipole moment per unit volume is called the polarization. So by del V. So if you divide it by per volume, it is called the polarization. Okay, polarization. So this diagram shows the dipole arrangement or dielectric material. So positive and negative charges separated by a distance D. That's all. Thank you.